Hello everyone, welcome to the Waveshare's ESP32 Arduino Getting Started tutorial. In the last lesson, we used the ADC on the ESP32 to read analog signals from a potentiometer and learned how to handle analog input. Now, conversely, how do we make the ESP32 output a continuous effect similar to an analog signal? For example, we don't just want to simply turn an LED on and off. We want to smoothly control its brightness, from completely off to slightly lit to the brightest. In this lesson, we will learn a key technology, pulse width modulation, and use it to create a breathing light effect. PWM, short for pulse width modulation, is an extremely clever technique. By rapidly switching a digital signal on and off and precisely controlling the proportion of high-level time within one cycle, it equivalently outputs a continuously varying average voltage. Essentially, it is still a digital signal with only two states, high-level and low-level. By precisely controlling the ratio of high-level time within a fixed cycle, it equivalently controls the average power delivered to the load. This ratio of high-level time to the total cycle duration is called the duty cycle. When the duty cycle is 0%, the signal is always low, the average voltage is 0 volt, and the LED is completely off. When the duty cycle is 20%, the signal is high for 1/5 of the cycle, so the average voltage is about 20% of 3.3 volt, and the LED glows dimly. As the duty cycle increases from 50% to 100%, the high level lasts longer, the average output voltage increases linearly, and the LED becomes brighter. When the duty cycle reaches 100%, the signal becomes continuously high, equivalent to directly outputting 3.3 volt, and the LED is at its brightest. Another core concept of PWM is frequency, which indicates how many PWM cycles repeat per second, measured in hertz. Choosing the right frequency is important. For example, for LED dimming, we need a high enough frequency so that the human eye's persistence of vision makes the LED appear to glow steadily and smoothly, without visible flicker. We use the LEDC PWM controller peripheral on the ESP32 to control LED brightness. Note that although it is called an LED controller, it can also generate general-purpose PWM signals to control other devices like servos. The ESP32 SoC integrates multiple LEDC channels. The exact number depends on the specific SoC model. Each channel can generate independent waveforms, meaning you can control multiple pins to output PWM signals with different frequencies and duty cycles simultaneously. In the Arduino programming environment, we mainly use it in two ways. The standard Arduino function, analogWrite. It is very convenient, letting you quickly implement functionality with minimal code without worrying about complex low-level configuration. The ESP32 specific LEDC API library. This provides richer, lower-level control, such as precisely setting PWM frequency, resolution, and channel. Next, we will use both methods to create a breathing light effect. Before programming, let's build an LED circuit. Components needed: one ESP32 development board, one breadboard, one LED, one 330 ohm resistor, a few jumper wires. Please follow the steps shown on the screen. 1. Find the longer leg of the LED. This is the anode. 2. Connect the anode through the 330 ohm current limiting resistor to GPIO 7 of the ESP32. 3. Connect the shorter cathode leg of the LED directly to a GND pin on the ESP32. Let's start with the simplest method, using analogWrite. This is the standard Arduino way to output PWM. You can find this code in our documentation. Its logic is very straightforward. In the loop function, we designed two for loops. The first loop increments the variable duty cycle from 0 to 255. Inside the loop body, we call the core function analogWrite. The analogWrite function takes two parameters. The first parameter, LED pin, specifies which pin to output PWM on. The second parameter, duty cycle, sets the PWM duty cycle. Here is a key point. Earlier, we described duty cycle as a percentage from 0% to 100%, but in code, we pass an integer from 0 to 255. This is because the program uses a specific integer range to represent 0 to 100% duty cycle. The size of this range depends on the PWM resolution. Arduino's analogWrite function uses an 8-bit resolution by default. meaning it divides a PWM period into 2 to the 8th equals 256 levels. So we use integers from 0 to 255 to describe the duty cycle. 0 corresponds to 0% duty cycle. 255 corresponds to 100% duty cycle. Around 127 corresponds to about 50% duty cycle. In programming, we often casually refer to this 0 to 255 setting value as the duty cycle. As duty cycle increases from 0 to 255, the LED smoothly brightens from off to maximum. The second for loop does the opposite, decreasing duty cycle from 255 down to 0, gradually dimming the LED. The two loops run alternately, creating the breathing light effect. Delay 10 controls the speed of brightness change. Try modifying this value and observe the effect. The advantage of using analogWrite is its simplicity and consistency with standard Arduino usage. It automatically handles PWM channel allocation, frequency, and resolution settings. Very convenient. Now upload the code and see the result. Now let's look at the second method, using the LEDC API on the ESP32. This approach gives us finer control over PWM. This method is slightly more complex and mainly involves two steps: initialization and writing the duty cycle. First, look at the setup function. Here we call LEDCAttach function to complete the PWM initialization. This function takes three parameters: LED pin, the pin we want to control; frequency, the PWM signal frequency. We set it to 5000 Hz, which is very smooth for an LED. Resolution, the PWM resolution. We set it to 8 bits, so the duty cycle range remains 0 to 255, making it easy to compare with the previous example. You can also set a higher resolution for more precise brightness control. After initialization, in the loop function, we use LEDCWrite to update the duty cycle. This function is very similar to analogWrite. The first parameter is the pin, the second is the duty cycle value. The rest of the program logic is identical to the previous example, again producing a breathing light effect. To summarize, analogWrite is simple to use and ideal for quickly implementing functionality. The LEDC API offers greater flexibility, making it a better choice when you need precise control over frequency and resolution. There are many other useful functions for the ESP32 LED controller. You can find their usage in the Arduino ESP32 documentation. We won't cover them all here. Now let's do a more interesting exercise, combining the analog input from the previous lesson with the PWM output from this lesson. Manually control the LED brightness in real time by turning a potentiometer. First, we need to add a potentiometer to the existing circuit. Connect the two outer pins of the potentiometer to 3.3 volts and GND, and the middle signal output pin to an ADC pin on the ESP32, for example, GPIO8. After connecting the circuit, let's examine the code. The core logic is in the loop function. We first read the potentiometer value using analogRead. As we know, the ESP32S3's ADC is 12-bit, so the reading ranges from 0 to 4095. However, the analogWrite function expects a duty cycle range of 0 to 255. These two ranges don't match. What should we do? This is where the map function comes in. Map proportionally maps a value from one range to another. Here, it linearly converts the potentiometer reading to the PWM required range. Finally, we use analogWrite to set the LED brightness with the computed brightness value. Upload the code and observe the results. As you turn the potentiometer, the LED brightness changes accordingly. Alright, that concludes this lesson. Let's quickly recap. We learned the basic principles of PWM, including the concepts of duty cycle and frequency. We practiced generating PWM signals on the ESP32 using both analogWrite and the dedicated LEDC API. Finally, through an extension exercise, we implemented potentiometer-controlled LED brightness. In the next lesson, we will learn about UART serial communication on the ESP32. Thank you for watching. See you in the next lesson.